Hey everyone, and welcome. Today, we're jumping into one of the coolest and most fundamental challenges in machine learning. It all boils down to a pretty simple question. How do you draw the absolute best line to separate two different groups of things? It sounds easy, but the answer is really elegant. Let's dive in.
Okay, so our journey starts with a really simple visual puzzle. Just imagine you've got a whole bunch of data points on a screen, and your one job is to draw a single line that cleanly splits everything into two distinct piles.
So take a look here. We've got our circles on one side, diamonds on the other. Now I could draw a line right here, or maybe squeeze one in here, or even way over here. I mean, technically they all work, right? They all manage to separate the two groups. But are all these lines really created equal? Nah, not even close. Some of these just feel better, more confident than others.
And that right there is the million-dollar question. When you have basically infinite possibilities, how in the world do you define and then find that one single perfect optimal line? What is it that makes one dividing line better than all the rest?
Well, here's the secret. It turns out we don't just want a line. What we really want is a buffer zone. The best line is the one that stays as far away from the points in both groups as possible. The best way to think about it is like this. You're trying to draw the widest possible street that separates the circles from the diamonds. Our winning line is the one that runs right down the middle of that super wide street.
So how do we actually find this widest street? For a job this important, we need a hero. We need an algorithm that is specifically built for this one task. And that algorithm, you've probably heard of it, is the legendary Support Vector Machine, or SVM for short.
You know, the logic behind an SVM is actually beautiful in its simplicity. First, it just looks at the data and identifies the two different classes. Then it gets to work finding that widest possible street, that margin between them. Step 3, it pinpoints the most important data points, the ones that are right on the edge of that street. And finally, boom, it draws the line right down the middle. That's our classifier.
And those points on the edge, they get a really cool name. They're called support vectors. This name is just perfect because it tells you exactly what they do. They are the only data points that matter for defining the line. Think about it. If you took any of the other points, the ones far away from the boundary, and moved them around, nothing would happen. The line wouldn't budge. But the second you move a support vector, the entire street has to shift. They literally support the entire decision boundary.
And really, that's the whole game right there. The one single goal of a support vector machine is to maximize the margin. That's it. So why is that so important? Well, a wider street means our classifier is way more robust. It's built in the biggest possible safety buffer, which means it's much less likely to get it wrong when it sees new data points that are kind of close to the boundary. It just generalizes better to the real world.
Okay, so far we've been living in a perfect little world where all our data is nice and cleanly separated. But let's be real, what happens when we have to deal with the messy, overlapping data we find in the real world?
Exactly. What if a circle decides to wander over into diamond territory? Or a diamond gets mixed in with the circles? If we demand a perfectly clean street with zero exceptions, we're just not going to be able to find a line at all. So does the whole idea just fall apart then?
No, not at all. This is where another really clever idea called hinge loss saves the day. You can think of it like a penalty system. The SVM basically says, okay, I'll allow some points to be inside the margin or even on the wrong side of the street completely, but I'm going to add a penalty every time that happens. This flexibility creates what's called a soft margin, and it's what lets the SVM find the best possible street even when the data is noisy and imperfect.
And what's so cool is that this whole way of thinking, this margin-based approach, is incredibly versatile. So far, we've been talking about support vector classification, or SVC, which is all about separating categories, like our circles and diamonds. But you can adapt the exact same logic for something called support vector regression, or SVR. Instead of separating groups, SVR uses that margin idea to predict a specific number, like the price of a house or the temperature tomorrow.
So we have this really powerful concept of maximizing a margin to find the perfect boundary. What does that actually let us do out there in the wild? Well, you'd be surprised. Let's look at some of the really powerful ways this is used.
First thing to know, don't think for a second that we're stuck with just two groups. This fundamental principle of finding the best separating boundary can be cleverly extended to handle problems with 3, 4, or even thousands of different categories. It's honestly kind of amazing. This one core idea, maximizing the margin, is the engine behind an incredible variety of real-world tools.
It's used for things like finding specific genes in the long strand of DNA, automatically adding tags to images, ranking the results you see in a search engine, and even figuring out the shortest, most efficient path through a complex network. It's everywhere. So in the end, it all comes back to this one beautifully simple concept. Find the widest, safest path you can between different groups. The support vector machine is just one incredible application of this idea. And it kind of leaves you with a final thought, right? Where else in our lives, in business, in science, or even just in our daily decisions, can this powerful idea of maximizing the margin help us find a little more clarity in a really complex world?